Last time we defined null space and range of a linear map. Today we prove the rank-nullity theorem. Domain dimension equals the dimension killed by the map plus the dimension visible in the range. So yes, dimension survives the trip through a linear map, but it comes back split into two receipts. Mathematics, naturally, demands accounting. Let V be finite dimensional, and let T be a linear map from V to W. Then the range of T is finite dimensional. And dimension V equals dimension null T plus dimension range T. The null space counts the directions destroyed by T. The range counts the directions that remain visible after T acts. The proof has one main move. Start with a basis of the null space, then extend it to a basis of V. First choose a basis U1 through UM of the null space. Then extend that list to a basis of V by adding V1 through Vn. We will prove that TV1 through Tvn is a basis of the range of T. Then the theorem becomes a counting statement. Naturally, the counting only works after the notation has made everyone nervous. Let us write the setup carefully. Because null T is a subspace of finite dimensional V, it has a basis. Call it U1 through UM. Extend that independent list to a basis of V by adding V1 through Vn. Every U vector is in the null space, so T sends each of them to 0. Now we prove that TV1 through Tvn spans the range. Take any vector W in the range. By definition, W equals T of X for some X in V. Since our long list is a basis of V, write X using the U vectors and the V vectors. Apply T linearity lets T distribute across the whole linear combination. But the U parts vanish. Because the U vectors are in the null space, what remains is a combination of TV1 through Tvn. Now we prove that those images are linearly independent. Suppose a linear combination of TV1 through Tvn equals 0. By linearity, this says T of the corresponding combination of V vectors is 0. So that combination of V vectors lies in the null space. Because the U vectors form a basis of the null space, that same vector can be written using the U vectors. Move everything to one side. We now have a linear combination of the basis of V equal to 0. Since that long list is a basis, all coefficients are 0. In particular, all the C coefficients are 0. We have shown that TV1 through Tvn is a basis of the range. The null space basis has length m. The range basis has length n. The full basis of V has length m plus n. Therefore dimension V equals dimension null T plus dimension range T. Rank nullity. At last. Without matrices barging into the room. Here is the same idea in a simple example. Let P send x, y, z to x, y. This forgets the z coordinate. The null space is the z-axis, which has dimension 1. The range is all of R2, which has dimension 2. Rank nullity says 3 equals 1 plus 2. Even arithmetic gets a cameo, lucky thing. Now the first corollary, a bigger finite dimensional space cannot inject into a smaller one. Assume dimension V is greater than dimension W. Rank nullity gives dimension null T equals dimension V minus dimension range T. But the range sits inside W, so its dimension is at most dimension W. Therefore the null space has positive dimension. So the null space contains non-zero vectors. By the injectivity test from last time, T is not injective. The second corollary is dual in spirit. A smaller finite dimensional space cannot map onto a bigger one. Assume dimension V is less than dimension W. Rank nullity gives dimension range T equals dimension V minus dimension null T. So dimension range T is at most dimension V, which is still less than dimension W. Thus the range cannot equal W, therefore T is not surjective. Let us summarize before rank nullity starts acting like it owns the entire chapter. Rank nullity splits the dimension of the domain into the dimension killed by T and the dimension visible in the range. The proof works by extending a basis of the null space to a basis of V. If the domain is bigger than the codomain, injectivity is impossible. If the domain is smaller than the codomain, surjectivity is impossible. Next time, we can start using rank nullity like a civilized counting machine, which is more than can be said for most machines.